The heat equation is a parabolic partial differential equation that describes the distribution of heat in a given region over time. Statement of the equation. For a function u of three spatial variables and the time variable t, the heat equation is more generally in any coordinate system, where alpha is a positive constant, and delta or 2 denotes the Laplace operator. In the physical problem of temperature variation, U is the temperature and alpha is the thermal diffusivity. For the mathematical treatment it is sufficient to consider the case alpha equals 1. Note that the state equation, given by the first law of thermodynamics, is written in the following form. This form is more general and particularly useful to recognize which property influences which term. The heat equation is of fundamental importance in diverse scientific fields. In mathematics, it is the prototypical parabolic partial differential equation. In probability theory, the heat equation is connected with the study of Brownian motion via the Fokker-Planck equation. In financial mathematics it is used to solve the Black-Scholes partial differential equation. The diffusion equation, a more general version of the heat equation, arises in connection with the study of chemical diffusion and other related processes. General description. Suppose one has a function u that describes the temperature at a given location. This function will change over time as heat spreads throughout space. The heat equation is used to determine the change in the function u over time. The rate of change of u is proportional to the curvature of u. Thus, the sharper the corner, the faster it is rounded off. Over time, the tendency is for peaks to be eroded, and valleys filled in. If u is linear in space at a given point, then u has reached steady state and is unchanging at this point. The image to the right is animated and describes the way heat changes in time along a metal bar. One of the interesting properties of the heat equation is the maximum principle that says that the maximum value of u is either earlier in time than the region of concern or on the edge of the region of concern. This is essentially saying that temperature comes either from some source or from earlier in time because heat permeates but is not created from nothingness. This is a property of parabolic partial differential equations and is not difficult to prove mathematically. Another interesting property is that even if u has a discontinuity at an initial time t equals t0, the temperature becomes smooth as soon as t greater than t0. For example, if a bar of metal has temperature 0 and another has temperature 100 and they are struck together end to end, then very quickly the temperature at the point of connection will become 50 and the graph of the temperature will run smoothly from 0 to 100. The heat equation is used in probability and describes random walks. It is also applied in financial mathematics for this reason. It is also important in Riemannian geometry and thus topology. It was adapted by Richard Hamilton when he defined the Ricci flow that was later used by Grigory Perelman to solve the topological Poincaré conjecture. The physical problem and the equation. Derivation in one dimension. The heat equation is derived from Fourier's law and conservation of energy. By Fourier's law, the rate of flow of heat energy per unit area through a surface is proportional to the negative temperature gradient across the surface, where K is the thermal conductivity and U is the temperature. In one dimension, the gradient is an ordinary spatial derivative, and so Fourier's law is in the absence of work done. A change in internal energy per unit volume in the material, delta Q, is proportional to the change in temperature, delta U. That is, where Cp is the specific heat capacity and ρ is the mass density of the material. Choosing zero energy at absolute zero temperature. This can be rewritten as the increase in internal energy in a small spatial region of the material over the time period is given by where the fundamental theorem of calculus was used. If no work is done and there are neither heat sources nor sinks, the change in internal energy in the interval x minus delta x plus delta x is accounted for entirely by the flux of heat across the boundaries. By Fourier's law, this is again by the fundamental theorem of calculus. by conservation of energy. This is true for any rectangle, t minus delta t, t plus delta t, times x minus delta x, x plus delta x. By the fundamental lemma of the calculus of variations, the integrand must vanish identically, which can be rewritten as, or, which is the heat equation, where the coefficient is called the thermal diffusivity. An additional term may be introduced into the equation to account for radiative loss of heat, which depends upon the excess temperature U equals T minus T's at a given point compared with the surroundings. At low excess temperatures, the radiative loss is approximately μU, giving a one-dimensional heat transfer equation of the form at high excess temperatures. However, the Stefan-Boltzmann law gives a net radiative heat loss proportional to, and the above equation is inaccurate for large excess temperatures, giving a high-temperature heat transfer equation of the form where, here, sigma is Stefan's constant, epsilon is a characteristic constant of the material, P is the sectional perimeter of the bar and A is its cross-sectional area. However, using T instead of U gives a better approximation in this case. Three-dimensional problem in the special cases of wave propagation of heat in an isotropic and homogeneous medium in a three-dimensional space. This equation is where U equals U is temperature as a function of space and time, is the rate of change of temperature at a point over time. UXX, UYY, and UZZ are the second spatial derivatives of temperature in the x, y, and z directions, respectively. Is the thermal diffusivity, a material-specific quantity depending on the thermal conductivity K, the mass density ρ, and the specific heat capacity Cp. The heat equation is a consequence of Fourier's law of conduction. If the medium is not the whole space, in order to solve the heat equation uniquely we also need to specify boundary conditions for U. To determine uniqueness of solutions in the whole space, it is necessary to assume an exponential bound on the growth of solutions. Solutions of the heat equation are characterized by a gradual smoothing of the initial temperature distribution by the flow of heat from warmer to colder areas of an object. Generally, many different states and starting conditions will tend toward the same stable equilibrium. As a consequence, to reverse the solution and conclude something about earlier times or initial conditions from the present heat distribution is very inaccurate except over the shortest of time periods. The heat equation is the prototypical example of a parabolic partial differential equation. Using the Laplace operator, the heat equation can be simplified and generalized to similar equations over spaces of arbitrary number of dimensions. As where the Laplace operator, delta or 2, the divergence of the gradient, is taken in the spatial variables. The heat equation governs heat diffusion, as well as other diffusive processes, such as particle diffusion or the propagation of action potential in nerve cells. Although they are not diffusive in nature, some quantum mechanics problems are also governed by a mathematical analog of the heat equation. It also can be used to model some phenomena arising in finance, like the black skulls or the Ornstein-Uhlenbeck processes. The equation, and various nonlinear analogues, has also been used in image analysis. The heat equation is, technically, in violation of special relativity, because its solutions involve instantaneous propagation of a disturbance. The part of the disturbance outside the forward light cone can usually be safely neglected, but if it is necessary to develop a reasonable speed for the transmission of heat, a hyperbolic problem should be considered instead, like a partial differential equation involving a second-order time derivative. Some models of nonlinear heat conduction have solutions with finite heat transmission speed. Internal heat generation. The function U above represents temperature of a body. Alternatively, it is sometimes convenient to change units and represent U as the heat density of a medium. Since heat density is proportional to temperature in a homogeneous medium, the heat equation is still obeyed in the new units. Suppose that a body obeys the heat equation and, in addition, generates its own heat per unit volume at a rate given by a known function Q varying in space and time. Then the heat per unit volume U satisfies an equation. For example, a tungsten light bulb filament generates heat, so it would have a positive non-zero value for Q when turned on. While the light is turned off, the value of Q for the tungsten filament would be zero. Solving the heat equation using Fourier series. The following solution technique for the heat equation was proposed by Joseph Fourier in his treatise Théorie analytique de la chaleur, published in 1822. Let us consider the heat equation for one space variable. This could be used to model heat conduction in a rod. The equation is where U equals U is a function of two variables x and t. Here x is the space variable, so x 0, L, where L is the length of the rod. T is the time variable, so t 0. We assume the initial condition where the function f is given, and the boundary conditions. Let us attempt to find a solution of that is not identically 0, satisfying the boundary conditions but with the following property. U is a product in which the dependence of U on x, t is separated, that is, this solution technique is called separation of variables. Substituting U back into equation, since the right-hand side depends only on x and the left-hand side only on t, both sides are equal to some constant value minus lambda. Thus, and we will now show that non-trivial solutions for values of lambda 0 cannot occur. Suppose that lambda less than 0. Then there exist real numbers b, c such that from we get x equals 0 equals x and therefore b equals 0 equals c, which implies u is identically 0. Suppose that lambda equals 0. Then there exist real numbers b, c such that x equals bx plus c. From equation we conclude in the same manner as in 1 that u is identically 0. Therefore, it must be the case that lambda greater than 0. Then there exist real numbers a, b, c such that and from we get c equals 0 and that for some positive integer n. This solves the heat equation in the special case that the dependence of U has the special form. In general, the sum of solutions to that satisfy the boundary conditions also satisfies n. We can show that the solution to, and is given by where other closed-form solutions are available. Generalizing the solution technique. The solution technique used above can be greatly extended to many other types of equations. The idea is that the operator uxx with the zero boundary conditions can be represented in terms of its eigenvectors. This leads naturally to one of the basic ideas of the spectral theory of linear self-adjoint operators. Consider the linear operator delta U equals uxx. The infinite sequence of functions for n1 eigenvectors of delta. Indeed, moreover, any eigenvector f of delta with the boundary conditions f equals 0 is of the form n for some n1. The functions n for n1 form an orthonormal sequence with respect to a certain inner product on the space of real-valued functions on 0, L. This means finally, the sequence n spans a dense linear subspace of L2. This shows that in effect we have diagonalized the operator delta. Heat conduction in non-homogeneous anisotropic media. In general, the study of heat conduction is based on several principles. Heat flow is a form of energy flow, and as such it is meaningful to speak of the time rate of flow of heat into a region of space. The time rate of heat flow into a region 5 is given by a time-dependent quantity quart. We assume Q has a density, so that heat flow is a time-dependent vector function h characterized as follows. The time rate of heat flowing through an infinitesimal surface element with area ds and with unit normal vector n is. Thus the rate of heat flow into V is also given by the surface integral where n is the outward-pointing normal vector at x. The Fourier law states that heat energy flow has the following linear dependence on the temperature gradient, where A is a 3 times 3 real matrix that is symmetric and positive definite. By the divergence theorem, the previous surface integral for heat flow into V can be transformed into the volume integral. The time rate of temperature change at x is proportional to the heat flowing into an infinitesimal volume element, where the constant of proportionality is dependent on a constant kappa. Putting these equations together gives the general equation of heat flow. Remarks. The coefficient kappa is the inverse of specific heat of the substance at x times density of the substance at x. In the case of an isotropic medium, the matrix A is a scalar matrix equal to thermal conductivity. In the anisotropic case where the coefficient matrix A is not scalar, then an explicit formula for the solution of the heat equation can seldom be written down, though it is usually possible to consider the associated abstract Cauchy problem and show that it is a well-posed problem or to show some qualitative properties. This is usually done by one-parameter semigroups theory. For instance, if A is a symmetric matrix, then the elliptic operator defined by is self-adjoint and dissipative, thus by the spectral theorem it generates a one-parameter semigroup.